So, as he pointed out, use MATLAB. So we use the MATLAB over here. Actually, not we. Professor Yang-Hann Kim used MATLAB to draw this. Okay, this is drawn in dB scale. Therefore, we have a minus. Minus 20 means what? I look at his calculation, and I find out he used 20 log of that value. Therefore, minus 20 means 10 to the minus 1/10. Right? Okay. So, this one corresponds to damping ratio 0.01, and then 0.05, 0.01, 0.1, 0.2, 0.5. So, as the damping increase, this curve goes up. Okay, that's what we can expect. Right? As damping increase of single degree of freedom system, this curve goes up. And this curve goes down. Okay? Right? And interestingly, as one student pointed out, you see that there is a 2 point, let's not move. Okay? The very similar things we found for a single degree of freedom system when we have a mass and the stiffness and damping, and we have base excitation. We have a point where the square root 2 magnitude of square root 2 is preserved, right? So, when you increase the damping, we have smoother curve, meaning that when we have operation frequency varies somewhere over here, and you still have small vibration. In this case, you have a very small vibration, but as soon as we deviated the frequency from this natural frequency a little bit, we will have a big increase of vibration. So it's not likely acceptable in designing vibration observer, right? Right? When you leave your partner, you don't behave like this, right? When you have a good food, you're delighted, and when you have some little difference in the food, then you're angry, right? It's not good, right? You behave like the system that you have a smooth behavior no matter what kind of dinner you have, right? So, normally we would like to have a smoother curve. So, this would be better. But if you increase the damping, you will have this. If you further increase the damping, then you might have something like this. Maybe you want to have this kind of curve in some case. That is actually Professor Dan Hartog's design solution. Professor Dan Hartog was the professor of my professor. Yeah. My supervisor's advisor. Okay. So he get the idea from this two invariant point, and then he thought that, hey, if I increase the damping somehow, then I would be able to have a very smooth curve that I may want to have in vibration. Where did he apply that vibration observer? You see, in old days there is a hair cutter, right? Right? Hair cutter experience many different excitation frequency, right? Theta, theta, what? Huh? So operation frequency is varying. And also is impact, right? Impact means we have many vibrations. Right? So he would like to put some vibration observer in a haircut using that concept. And he was quite famous because of doing this. Okay. That can be done. If you see this in linear scale, it's not interesting at all. Linear scale. So seeing dB scale is very physically very sensible, because we are looking at very details what's going on happening in the frequency range that we have interest. Okay. So let's move to other case. So vibration observer that has only damper. Only damper. Is it realistic? Yes, yes. For example, when you have rotating machine, okay, suppose you have a rotating machine, and if you want to reduce rotating machine by putting some fluid over there, then fluid can be modeled as the element that can provide a damper, right? Actually, there is a damper which we call how you call it in French? Lunch. No. Not Korean. English. Lanchester, okay, Lanchester damper. That was quite often used very often in old days, but no more. In these days, we are using not Lanchester type, but different type. For the Lanchester case, we have this matrix and this, and the K matrix look like this. And then we can get a solution, and we can draw it, and we can certainly pick up the appropriate parameter we want to have using this graph, okay? Using MATLAB. And I will give this slide to you, so don't worry. So, we have optimization problem. That means we have this function. Uh-oh. Second.